The crankshaft connecting rod and bearings must be soundly constructed since they comprise one of the most highly stressed systems in an engine. The crankshaft has been called the backbone of the engine, and indeed it is. Because the crankshaft is such a critical item, its design and manufacture receives more care and attention than nearly any other major engine component. But what is the function of the crankshaft, and why is it so critical? The crankshaft converts the up and down motion of the pistons into rotary motion, which can be transmitted through the drivetrain. In doing so, the crankshaft is subjected to tremendous twisting forces as well as bending forces as it turns. Further, it is subject to fatigue since it accumulates many cycles of stress in a short period of time and will rotate millions of times in the life of the engine. This rotation makes proper balance critical. Lastly, it must not generate excessive heat from friction between itself and the bearings, yet it must be able to withstand the heat that does build up. Thus, a crankshaft must be made from a material which can stand up to loading, yet minimize friction. To withstand these conditions, all Caterpillar crankshafts are produced from forged steel. Forgings maintain the natural flow lines of the metal so that they follow the crank contour. They are also heat treated to increase the hardness and strength as required. Finally, journal dimensions are closely controlled in the range of plus or minus 8/10,000ths of an inch, and bearing surfaces polished to a surface finish of 10 millionths. All of this is necessary to produce a crankshaft which will perform well over a long service life. Increased friction and increased bearing wear, or even seizure, could occur if the surfaces were not polished this finely. Significant problems or reduced bearing life could result from a journal surface polished above 10 millionths of an inch. Earlier, it was stated that a great deal of care goes into the manufacture of crankshafts. So, let's take a look at how it's done. The crankshafts begin as rough forgings, received from suppliers who have produced them to meet Caterpillar specifications. Caterpillar uses stringent criteria in selecting suppliers. We'll review these criteria later. They are then rough machined. Various oil passages are drilled, and facing operations are performed on the flanges. Semi-finish machining results in journals which closely approximate final dimensions. But possible distortion in the ensuing heat treatment prevents exact machining. The heat treatment of crankshafts must be performed properly, or insufficient strength and wear life will result. Proper heat treatment is a way to get the most strength out of a certain amount of material. This means that a more compact engine can be made. The heat treatment process developed by Caterpillar increases the hardness and fatigue strength of the areas of the crankshaft that require it for strength and wear resistance. In one type of heat treatment process, the entire crankshaft is heated to a red color. At this point, the steel changes its microstructure. The crankshaft is then quenched. In this treatment, the journal and fillet areas of the crankshaft receive the brunt of the quench. In other words, these surfaces of the crankshaft gain the benefits of the heat treatment. At present, the 1.1 liter 3200, 3300, 3176, 3400, and 3508 engines have this type of heat treatment. It is important that these crankshafts are not replaced with a shot-peened crankshaft that competitors may offer. The shot-peened crankshaft is not as strong as our heat-treated crankshaft, and the customer may run a risk of not having enough strength for the operation. A different type of heat treat process is used on our larger crankshafts, since their physical size makes the overall heating and quenching impractical. The journals of these crankshafts are selectively heated with induction coils and then quenched, while the remaining areas are shot-peened for improved fatigue life. The shot-peening process consists of hurling thousands of steel pellets against the metal, leaving the surface in a residual state of compression. This compressive residual stress caused by shot-peening tends to offset the tensile stress applied by a load or bending movement. Tensile stress has a tendency to cause fatigue cracks. As the shot peening and resulting residual compressive stresses offset the tensile stresses, the fatigue strength of the crankshaft is enhanced. Crankshafts are then finish ground and journals are polished to an exacting finish. Final dimensional tolerances of the journals are in the range of plus or minus 8/10,000ths of an inch, while surface finishes are always less than 10 microinches or 0.25 microns. Here we see the crankshaft being balanced. Holes are drilled in the counterweights to balance the crankshaft. By balancing the crankshaft dynamically, Caterpillar also achieves static balance. This is similar to a tire, where dynamic balancing of a crankshaft corresponds to a spin-balanced tire. To preserve all critical dimensions during storage, crankshafts are oiled, wrapped, and packaged in crates before leaving the plant. We've seen how Caterpillar manufactures crankshafts, but what about servicing or replacement at engine overhaul? Since a crankshaft is an expensive item, most customers prefer not to replace their crankshaft if at all possible. The regrinding of a crankshaft is a fairly common practice at major engine overhaul time. Caterpillar has become increasingly aware of the importance of quality reground crankshafts. So Caterpillar has developed the remanufactured exchange crankshaft program, covering many engines. Field-returned crankshafts are ground under size at the Corinth remanufacturing facility and meet new crankshaft specifications in all other ways. These remanufactured exchange crankshafts can be ordered like any new part. A core charge, similar to a bottle deposit, is assessed at invoicing, but it is refunded upon receipt of a worn crankshaft suitable for remanufacturing. A partial core credit is given for a returned damaged core suitable for remanufacturing. Anytime a customer orders a remanufactured crankshaft, a worn core must be returned to Caterpillar to be remanufactured. Production crankshafts from Mossville, which do not meet standard journal specifications, are also remanufactured at Corinth. Caterpillar operates the remanufactured crankshaft program as exchange and recommends that the program be investigated before resorting to a new crankshaft. Doing so will reduce owning and operating costs for customers, helping generate repeat sales. Competition in crankshafts stems from the rebuilding and regrinding of crankshafts. Power Engineering, Denver, Colorado; American Crankshaft, Charlotte, North Carolina; Northwest Motor Welding, Los Angeles; Cleveland Hone, East Lake, Ohio; and Swick Guth, McPherson, Kansas, are all very active in rebuilding or regrinding crankshafts. Many of these competitors will rebuild the crankshaft journals to the original dimensions via welding or chrome plating, in addition to grinding under size. Caterpillar does not employ these build-up techniques for several reasons. Chrome plating is brittle, and cracks can often develop on the journals. Likewise, adding metal by welding may not always result in a metal-to-metal bond of suitable integrity. Further, the rotation of the crankshaft causes stresses which try to pull this outside layer away from the base metal, and failure of a bearing or the crankshaft will result. Caterpillar Research has been studying improved techniques for building up journal surfaces, but does not yet believe that sufficient commercial progress has been made. Only when technology has made such advances will Caterpillar engineers endorse the use of built-up crankshafts. Other considerations become important when crankshafts are rebuilt by competitors. As mentioned earlier, the surface finish on the journals is critical. In addition, the radii where the journals blend into the webs must be properly maintained, or the crankshaft may break at any of those points. Last, additional heat treating or shot peening might be required, and these steps may be omitted or incorrectly performed. In all cases, customers should be made aware of the risks they take when having crankshafts rebuilt by competitors. Let's discuss the importance of balance and vibration dampening in diesel engines. First of all, we would like to cover balancers. Balancers, usually found on 4-cylinder and 60-degree V8 engines, counteract the shaking forces caused by the reciprocating motion of the pistons. The balancer shown here is built into the gear train. It is called a first-order balancer because it moves as fast as the engine. These gear-driven balancer shafts are called second-order balancers because they move twice as fast as the engine. While often confused, the balancer shafts shown on the left are not the same thing as the vibration dampener on the right. The vibration dampener controls crankshaft oscillation by smoothing the impulses caused by pistons firing at spaced intervals along the crankshaft. A vibration dampener of some type is found on all Caterpillar engines. The vibration dampener is usually mounted on the front of the crankshaft. Caterpillar uses two types of vibration dampeners, rubber and viscous. The rubber dampener, shown on the left, absorbs vibrations via its natural elastic properties, converting the energy to heat. The viscous dampener on the right suspends this heavy ring-shaped weight in a fluid which acts much like a fluid shock absorber. We've been discussing some of the forces which affect the crankshaft. Keep in mind the connecting rods are the components which transmit these forces. Connecting rods must withstand tremendous compressive loads hundreds of times per minute. Like the crankshaft, this repetitive loading makes fatigue strength an important consideration in the design of connecting rods. Finally, connecting rods must be balanced and weight controlled. Excessive vibrations occur if the con rods vary in weight. Therefore, Caterpillar controls the weight of its rods. Since so many design considerations are common to both crankshafts and connecting rods, it's not surprising that connecting rods are also forged. Alloy steels are used so that subsequent heat treatment will through-harden the rod. Dimensionally, our connecting rods are very similar to the I-beam shape commonly found in the construction industry, which has been proven many times over to give excellent strength while keeping weight to a minimum. In addition, shot peening is employed to improve fatigue resistance. Let's take a look at the production of con rods at the Mossville engine plant. Caterpillar heat treats and shot peens the forgings received from suppliers for impact strength and fatigue resistance. The sides are milled flat, the ends are bored, and the bearing caps are cut. Following finish machining, the eye bore, or piston end, must be expanded via heating so that the bushing can be assembled. Each rod is then individually machined to exact weight. This step also accomplishes the weight control referred to earlier. In much the same way as with crankshafts, our primary competition in connecting rods comes from rebuilders. While Caterpillar offers both new and remanufactured rods, and dealers offer rebuilt rods, the competition usually offers only rebuilt rods. Power Engineering, Swick-Guth, Cleveland Hone, and many smaller local machine shops will rebuild Caterpillar connecting rods. While not as difficult to rebuild as crankshafts, an improperly machined connecting rod can cause increased wear and damage to the engine. Likewise, failure to maintain appropriate weight control can also affect engine performance by causing excessive vibration. Working with the crankshaft and the connecting rod are some extremely important components: the rod bearing and the crankshaft or main bearing. Since bearing failures usually result in damage to related components, such as expensive crankshafts, a well-designed bearing is essential. Most modern bearing designs are a compromise between a desire to conform closely to the journal profile, minimizing friction, yet provide enough strength to prevent the bearing from collapsing under load. Earlier diesel engines minimized friction with bearings made from babbitt, a lead tin and antimony alloy. A babbitt bearing is very soft, however, and incapable of supporting heavy loads. Faced with this need, Caterpillar pioneered the commercial use of aluminum bearings in 1946. Aluminum alloy more closely approaches the strength of steel without greatly sacrificing embeddability and reduction of friction. Steel would be a good material from a strength standpoint, but a steel bearing against a steel crankshaft would generate too much friction. Embeddability refers to the ability to embed or accept small pieces of metal or debris so it won't damage the journals. As engine speeds and horsepower continued to increase, further bearing improvements were needed. The tri-metal bearings in current use combine the best properties of all three metals. The steel backing gives the composite bearing sufficient rigidity, while the lead-tin overlay exhibits superior embeddability and lubrication. A flash plating of tin is added to the overlay to inhibit corrosion, which can take place during storage or as a result of accumulated crankcase gases. The lead, tin, and steel are bonded to an aluminum center, which is hard enough for extreme service and resists acids which build up in the oil. A copper bonding material is normally used to assure that the layers are adequately bonded. Since bearings are purchased finished items, Caterpillar runs a great many quality control checks to monitor vendor quality. Among these are overlay blister tests run at 350 degrees Fahrenheit, hardness and thickness tests, a crush test done under load for dimensional control, and laboratory tests which simulate actual field conditions. It is impossible to run these destructive tests on each and every bearing, but sophisticated statistical sampling is employed to help monitor supplier conformance to specifications. In the past, these tests have resulted in the rejection of thousands of bearings. Several suppliers have experienced problems meeting specifications. As a result of these rejections, shortages resulted. But Caterpillar would rather have these shortages than permit inferior bearings into our distribution network. Today, through extensive work between engineering, quality assurance, and purchasing, Caterpillar is confident that they provide the best engine bearing available to our customers. Competition for replacement engine bearings is widespread. Most notable are Federal Mogul, Imperial Clevite, IPD, and TRW. Since bearings are a seemingly simple item, the temptation is great for our engine users to source non-OEM replacement parts. As we've seen, however, bearings are actually quite complex, and early failure can spell disaster. Caterpillar's competitive test program has shown that competitive replacement bearings do not always meet Caterpillar specifications. Some lack the lead-tin overlay altogether. Some bearings possessing the overlay have not been flash-plated with tin. The thickness and bonding of layers often varies. And finally, dimensions are not always correct. This last point is critical. Since competitors do not have access to Caterpillar specifications, they may loosen their tolerances in copying Caterpillar's design. The bearings shown in this slide were only 0.02 of an inch off size, yet the disaster was instantaneous. Can our engine customers stand for catastrophic failures such as this? Save them the expense of unnecessary or premature overhauls by insisting that they use genuine Caterpillar replacement parts. Point out the details that really do make a difference.